Hello, everybody, and welcome to the 27th session of IEEE VR 2020. This is the audio session. We will have 4 papers. The first paper is entitled Superhuman Hearing, Virtual Prototyping of Artificial Hearing, a case studies on interaction and acoustic beamforming. And this is a paper authored by Michele Geronazzo, Luis Vieira, Nils Nilsson, Jesper Olsen, and Stefania Serafin from Aalborg University in Copenhagen and Jabra in Denmark. And there will be myself, Stefania Serafin, who will be both chairing this session and also present the first paper. Hello, everybody. In this paper, we present superhuman hearing, virtual prototyping of artificial hearing, a case study on interaction and acoustic beamforming. This research is a collaboration between researchers from the Multisensory Experience Lab at Aalborg University in Copenhagen and researchers from a company called GN Resound, which is specialized in building hearing aids of the future. So the main motivation behind this research is that most hearing aids are designed by taking into consideration only the unimodal sense of hearing. But the hearing is actually a multisensory experience. What we see affects strongly what we hear and vice versa. And also the way we move affects what we hear. So can we actually test hearing aids and design hearing aids based on the fact that humans are inherently multisensory creatures? And obviously, one of the tools that can be used to design better hearing aids is virtual reality prototyping. So one of the challenges in designing hearing aids is how to design what is called a beamform. So as you can see in this picture, a beamform is basically like a zoom on a specific auditory event. And this is what we are trying to do in this research. How to improve the design of beamforming for hearing aids in virtual reality. So this paper addresses 2 topics: how users of virtual reality technologies interact with auditory events, specifically speech, and how to design this auditory event in order to give humans the ability of having super hearing. Imagine, for example, that you are in the middle of a conversation and you want to be able to zoom on a specific person which is saying something to someone else. So can you actually not only provide the hearing impaired users to the ability of hearing, but also humans with so-called normal hearing, can you improve their hearing capabilities? So in order to obtain some sort of super hearing. So in order to achieve this goal, we created 2 scenarios. One virtual scenarios where we have only a abstract virtual reality environment with 8 cubes placed in a circle, and another more realistic scenario where 8 users alternating between male and female were placed in an anechoic chamber. Each of them they were provided with a clip microphone, and they were asked to repeat in a loop some sentences. These sentences, they were taken by the IEEE database of speech sentences, which are heavily used for testing hearing aids. And this, of course, is still an abstract scenario, because in everyday life you don't find 8 people saying pretty much the same sentence all over, but it is closer to an ecological settings. Like, think of the classic cocktail party problem where you have several people at a cocktail party talking at the same time, and how can you focus on one of them? So, and these are our 3 research questions then. What are the main preferences for directivity parameters? And I will explain in a second which parameters we could modify and how. Can users modulate their performance in the presence of realistic visual references? And also, will users' performance differ between interaction techniques? So specifically, this is our setup. We used a HTC Vive with embedded Pupil Lab AI tracker because we were testing 3 different interaction techniques. One interaction technique, which is simply consists on turning the head to the user that one wants to focus on. Another interaction technique, which is a combination of looking at a person while turning the head. And then the third interaction technique, which makes use of the HTC Vive tracker. So just using the controller and pointing at specific speakers. So for the sound rendering, we used Google Resonance Audio, and we used also a database of HRTFs, which is available for the dummy head Neumann FU100, and it's a part of the SADI database of HRTF. And we used the third order ambisonic. So in order to control the parameters, so we have 3 parameters that the test subjects are able to control. One parameter is the gain level, so between -20 and 20 decibel. So this is the level of the sound source. Then sharpness, which is how sharp is the beam on a scale between 1 and 10. And the equation that you can see, P of theta there, is the equation that shows how the different parameters are connected. Alpha is the directivity. So we can change it from 0, which is an omnidirectional pattern, to 1, which is a bipolar pattern. So these 3 parameters, they can be controlled independently using the HTC Vive controller, as you can see on the right side of this picture. And this is the first set of the experiment, the calibration, where the user finds the optimal set of parameters. So as you can see here, this is the first experiment where only abstract sources are used. So this is the scenario the user is exposed to. So cubes in a circle, and the position of the cubes is the same as the position of the people in the experiment based on 360 video. And so this is the first experiment, the duration of the different parts. So first there is a training part, and then there is the first pairing task. So in both experiments, the task was to find the pair of speakers that were saying the same sentence. And then after that, there was some post-experimental questionnaire. In the second experiment, as I mentioned, so the task is also to find the pair of speakers among the 8 speakers, and but in this case, subjects are exposed to 360-degree captured characters. And this is the task of the second experiment, so finding the pairs. And then also they were exposed in this case to 3 questionnaires. Again, the NASA questionnaire, but also a user experience, 2 different user experience questionnaires. So here we're going to see the results. So first of all, we can see that these 3 representations, they show the way the subjects, they were calibrating the parameters. So it is noticeable mostly from these graphs is how subjects, they didn't really modify the alpha parameter and the sharpness, but they mostly modified the gain. So in order to calibrate, they relied mostly on the gain of the sound sources. Then what we can see from these graphs is the pairing times for on top of the three graphs show pairing times for the three conditions. So H represents the condition where they were moving the head. HE is the condition where they were using head and eye tracking together. And then the last condition is where they were using the controller. What is noticeable in these graphs is how the subjects use a significant larger amount of time to find the first pairs in all three conditions. But then once the first pair was decided, then the rest of the experiment was done quite fast. And as I mentioned, this is the same for all three conditions. Then we can see what is the amount of correct pairings. So as expected, the performance of the subjects is better in the case where realistic stimuli, those are the ones depicted here in blue, are provided as opposed to abstract stimuli. And when we look at the score from the NASA questionnaire, we do not see any significant difference. This is the plot that you can see on the bottom right of the figure. And what that shows is basically that the three conditions, the subjects, they didn't really find a condition which was more usable and than the others. And same for usability score. This is the usability score for the three conditions. As you can see, the usability was rated in a scale from 1 to 5, and there is no significant difference among the head interaction, the eye interaction, or the head with controller interaction. And the same we can say for the quasi-score. So also in that case, as you can see, there is not really a condition, an interaction technique, which can be considered as more usable than the others. So there is no significant difference measured between the three conditions. So this concludes my presentation. What we can say is that in general, the experiments show that maybe an easier task should have been given to the subjects because it was very hard for them to pair the correct pairs, and nobody actually completely concluded the task successfully. But this experiment gives us a nice indication on how hearing of the future can be constructed and how interaction techniques can help in the design of multisensory hearing experiences. Okay, so we have time for some questions, and I would like to encourage the audience actually to post their questions in Slido also for the next 3 talks. I can see we have 4 questions. Probably we have time to take a couple of them. So let's take them chronologically. And I would also encourage you to join the speakers in the hubs after the talk, so there can be more discussions on audio related topics. This session has one talk less than the other, so there's probably some time before lunch, depending on your time zone, to have some discussions. So the first talk is how can this work be used for designing hearing aids? So this work was actually a collaboration with a company in Denmark called GN Resound, and it was the work of a master student, Luis Vieira. And the way the companies want to use this research is to design the hearing aids of the future, in the sense that nowadays hearing aids, they're not considered like a cool device, and the main goal is to provide so-called normal hearing, so enable hearing impaired to hear like a normal person, quote unquote. But ideally, hearing aids, and that comes the title of the paper, would also enable super hearing. So you can hear even better than a so-called normal person. And how can you empower this? How can you, for example, have a audio Zoom? How would you design it? Which kind of interaction? So this is why the study looks both at the audio Zoom side, but also the interaction side, which is probably both a plus and but also a limitation, because maybe we try to do too much in this paper. That's why also there are not results which are so strong. Maybe I have time to take a second question, and then we can move to the second speaker. So nice work. Could you give some comments on how powerful was the beamformer and how hard was the task? Yeah, so the task was actually very hard. The beamformer was not uh, clearly indicating the pair of speakers. Actually, some of the a couple of participants actually stopped the task because they found it simply impossible to complete. So it was really challenging for the listeners, especially as you can see from the results. The first pair of speakers, they were the ones that were harder to determine. So it was not really a clear, and none of the participants performed perfectly the task. So it was a hard hearing task that clearly hearing impaired would not be able to perform as it is right now. So the beamformer needs to be improved and be stronger if it has to used for this superhuman hearing. Okay, so as I mentioned, we have no further time for questions, but we can take more questions later at the end of the presentation in the hubs. And maybe we can move to the second presentation. So the second presentation is entitled Scene-Aware Audio Rendering via Deep Acoustic Analysis. And the presentation will be given by Zhenyu Chang.
Hi everyone, this is Zhenyu from the University of Maryland. I'm here to present our work on scene-aware audio rendering via deep acoustic analysis. We highly recommend you wearing a good headset prior to listening to our audio demos in this talk. First, I want to introduce you some important real-world acoustic effects that we hear every day. One of them is room reverberation. Reverberation is the effect of sound reflecting within the room environment, causing the original sound to last longer. I'll play two audio clips. The first is the clean sound that's no reverberation at all.
Buck did not read the newspapers, or he would have known that trouble was brewing.
The other is the reverberant version.
Buck did not read the newspapers, or he would have known that trouble was brewing.
Intuitively, reverberation time, also denoted as T60, describes how reverberant an environment is. The longer the reverberation time, the more reverberant the sound is. I have three audio examples here showing you impulse responses of increasing reverberation time. If you walk around in your house, you might notice now that your bedroom can have a very different reverberation time compared with the kitchen. The second effect is called room equalization. You might know that vibrating objects have their intrinsic resonance frequencies. Similarly, the air vibrations in a room can have frequencies that are reinforced or damped depending on the shape of the room. We call these room modes, and they produce characteristic equalization of a room. The red arrows on the right figure denotes that frequencies that are significantly modified by the room equalization. I also play two audio clips non-stoppingly to show you how room EQ makes the sound different.
I am sitting in the morning at the diner on the corner. I am sitting in the morning at the diner on the corner.
The second one sounds a little bit more gloomy, right? Note these two recordings, they have the same T60, but they still feel quite different. But are these effects important at all? It depends. Nowadays, many virtual reality games have started using 3D audio rendering engines. But if you're talking about augmented reality, no such system exists. We need to blend synthetic sound with real sound, and that is more challenging. And we believe that mismatched sound in AR degrades user experiences, so we want a fix there. But before I jump into our work, let me give you some background on the problem we're facing. I'll start with sound propagation in the virtual world. One thing you need is the room geometry, which is easy to acquire with modern computer vision techniques, which we don't discuss in this talk. Another important thing you need is the acoustic materials. We need to assign these materials to each surfaces in the environment, and they will determine how much energy of sound is reflected upon each bounce. Once you have these ready, you can use ray tracing engines to simulate the propagation of sound and get realistic sound rendering. However, the most difficult part in the pipeline is to get correct acoustic materials that make your simulated sound consistent with the real world. Some prior work on acoustic material acquisition also rely on vision-based methods. However, purely vision-based method cannot reliably determine the acoustic materials of various things because different acoustic materials can have the same appearance, which causes ambiguity. Even if the recognition is correct, the same type of material, for example, different carpets, they can also have different acoustic absorption coefficients. Therefore, only doing the visual recognition is not sufficient. A better way to correct materials is through acoustic measurement in the room environment. The fact is that both T60 and equalization can be measured from an impulse response. The measurement process utilizes a sine sweep audio, which plays the sound from 20 Hz to 20 kHz gradually. And I'll play this 10-second sine sweep right now. Just a warning, you can turn down your volume for now because this sweep signal can be a bit annoying to your ear. I'll play it now. So once you play and record the sine sweep in the room, usually for multiple times, you can deconvolve it to get the impulse response. And furthermore, the T60 and room equalization can be evaluated from that. Doing this can guarantee you good results, but as you have heard, this is not very comfortable and not very user-friendly process. It may not be doable for most novice users. Our goal in this work is to find a more user-friendly way that requires less effort from the user by doing more analysis on our side. The intuition here is that the reverberation time and the room equalization may be estimated from an arbitrarily recorded audio sample from the room. There are two major parts in our pipeline. First step is to do T60 and equalization estimation using our deep acoustic analysis network. Then we can perform reverberation simulation using geometric sound propagation. Note that we only require the user to provide a short speech recording in the room instead of the intrusive impulse response recording. In order to train a deep acoustic analysis network that can predict the T60 and room EQ, we need a large enough speech dataset with no impulse responses. We collect room impulse responses and clean human speech from various public datasets and mix them together strategically. The T60 and EQ labels are evaluated from original room impulse responses. We also perform augmentation on the training data in terms of T60 and equalization distribution. The final dataset size is 100K, which is further split into train, validation, and test sets. For network training, we use MEL spectrogram as input feature. Two networks are trained for EQ and T60 prediction independently. Note that prior work often trains the network to predict the full band T60s and use the same network for subband T60, but we consider subband T60 and EQ gains as a whole target, which achieves lower subband prediction errors. Our network is made compact to avoid overfitting. We are able to get T60 prediction error of 0.12 seconds and equalization prediction error of just 3.4 decibels. But are these small enough? We'll find out very soon. Let me go back to this sound rendering pipeline. Again, the story here is that you have the room geometry and acoustic materials. You can then run sound rendering in a forward simulation, but we also know that T60 can be evaluated from the simulation results, which means if you have target T60 that is different from your simulated T60, you can plug an iterative optimization scheme into this pipeline. So you can keep updating the material absorption coefficients until the simulated T60 is close to the desired one. By T60's mathematical definition, we are able to establish a relationship between the T60 and the material absorption coefficients. Then we directly use the T60 prediction from our network as input to our material optimizer with a constant objective function. Our optimization results shown in the right figure demonstrates the effectiveness of our method. Finally, we apply a linear phase filter for room equalization compensation, which completes our scene-aware audio rendering pipeline. Here are some quantitative results comparing our method, a prior measurement-based method, with the ground truth from 5 real-world room environments of different sizes. As you can see from the waveforms of simulated impulse responses, our results align closely to the ground truth and outperforms the prior method in time efficiency while maintaining comparable errors. We also have some qualitative results. We will play audio clips recorded in the real world along with our simulated results, as well as results from 3 prior work mentioned earlier. Please pay attention to the overall sound similarity with respect to the ground truth audio.
Infinitely many words can be written with a small set of letters. Infinitely many words can be written with a small set of letters. Infinitely many words can be written with a small set of letters. Infinitely many words can be written with a small set of letters. Infinitely many words can be written with a small set of letters.
The appearance of the island when I came on decks next morning was altogether changed. The appearance of the island when I came on decks next morning was altogether changed. The appearance of the island when I came on decks next morning was altogether changed. The appearance of the island when I came on decks next morning was altogether changed.
I just saw a gem near the new archaeological museum. I just saw a gem near the new archaeological museum. I just saw a gem near the new archaeological museum. I just saw a gem near the new archaeological museum.
In language, infinitely many words can be written with a small set of letters. In language, infinitely many words can be written with a small set of letters. In language, infinitely many words can be written with a small set of letters. In language, infinitely many words can be written with a small set of letters.
I believe my audience might feel different toward the audio just played, which is normal. But in order to understand how good our system works for general listeners, we conducted an online user study. asking our participants to listen to a list of audios and give their ratings based on their similarity with respect to the ground truth recording. The right side is a screenshot of the online study interface. We recruited 70 participants and followed the Mushra methodology. After collecting the data, we ran statistical analysis to understand the implications. We have multiple observations. Firstly, the overall quality of the prior measurement-based methods is better than our system, which is expected. Considering the fact we require much less input, especially without the intrusive impulse response measurement. Secondly, our full system with equalization filter compensation is better than without it. This demonstrates the usefulness of adding room EQ compensation. Lastly, our system is better than doing nothing and use some arbitrary material assignment with a flat EQ, which was used as the mean anchor in the study. In summary, our contribution includes a new pipeline to estimate, optimize, and render immersive audio in mixed reality applications, and we conducted a user study that validates the perceptual importance of our methods. There are a few things we haven't done in this work. For example, we don't consider speaker of microphone responses, which may need it to calibrate it if the device has a strong EQ. Also, we use the data-driven method, which may not work well for extreme acoustic conditions that we have not encountered. That concludes my talk. Thank you for your attention.
Okay, so thank you very much, Zenyu, for the nice presentation. And I can see we have some questions in Slido. So let's take them again chronologically. And so the first question is, nice idea. How can you account for dynamics in changes, such as moving occluders?
So as for moving occluders in the scene, first of all, we believe it does not significantly affect the impulse response or the equalization of the room. It's rather a property for the whole room. The impulse response, it does change, although we do recompute the impulse responses from frame to frame and apply the equalization filter again for each frame. So we think the dynamic occluders will not affect this pipeline much.
Thank you. Next question. This method is heavily related to the tracking data. Can this method be used for room acoustics with complex irregular objects?
That's a good question, because as I mentioned, this method, the deep acoustic analysis part is heavily related to the training data. So the data collection we've done is using real world data and impulse responses from two independent data sets. We use one of them as the training set, the other one as the test set. So actually the distribution of the train and test set is a bit different to test how good our system can generalize. And also in all the demos I've shown you, the rooms are not seen during the training stage. And we have seen some good results. That's the indication of some good generalization. Although I cannot deny that there are extreme conditions our method may not work well. For example, the irregular, I wouldn't say irregular objects. If the room environment is highly irregular, some strange music auditoriums, I don't know what can happen. And that can certainly be improved with better training data of better quality, I believe.
Thank you. Another anonymous question, and for those writing questions, feel free to write also your name. It's nice to know who is asking the question. But so are there any differences between the ray tracing technique used for global illumination and this one related to audio rendering? This is for it.
Yeah, audio rendering and visual rendering, they share a lot of techniques. The ray tracing part is pretty common, I would say. They are almost the same, except that when you collect the energy, you have to accumulate them to impulse response instead of a scalar intensity, whereas it's in visual rendering. There are a lot of technical differences, but I think most of the part are the same. Yeah.
Thanks. Since the talk was a bit shorter, we have time for another question, if you don't mind. Does the hardware of the system also play a role in the realism of the sound? And did you look into that?
Hardware of the system role in the realism of the sound. So if I understand correctly, you're saying it could sound different on different devices, and I would agree with that because each loudspeaker and the headset I'm wearing has its own responses, which may not be flat. So perceptually, it can be a bit different, but we didn't look into the effect of that. That might be future work.
Yeah, and I connected the last question is, does it work? Would it work also for bone conduction headphones?
Oh, that's a good idea, but I don't have much experience with bone conduction headsets. Sorry, I cannot answer that.
Okay, thank you very much for the presentation. And then we move to the third talk now, which is entitled Ear VR, using ear haptics in virtual reality for deaf and hard of hearing people. And the presentation will be given by Mohammad Reza Mirzel.
My name is Mohammad Reza Mirzai. I'm a PhD student at Vienna University of Technology, Institute of Visual Computing and Human-Centered Technology. In my presentation, I'm going to talk about a new prototype system called Ear VR that can be mounted on any desktop or mobile VR head-mounted display. This system can help deaf and hard of hearing people to feel and enjoy virtual reality, much like people without hearing problems. So, let's get into the presentation. According to a report from the World Federation of Deaf, there are more than 70 million people around the world with hearing problems. These people have a lot of limitations to use many of today's new technologies such as VR. In VR, 3D audio is a very important factor to increase the feeling of immersion. We know that VR provides great opportunities, especially for deaf and hard of hearing people, but they cannot interact very well in VR. Previous research showed that experience of deaf and hard of hearing people is different, and designing a special VR environment is required. For example, by adding symbols, subtitle, or live sign language translator. Based on recent studies, it's possible to use vibrotactile haptic devices to improve immersive VR experience among deaf and hard of hearing people. In this slide, you can see the prototype design of the Ear VR. Ear VR has two main sections. The processing unit that includes an Arduino, and we mounted it on top of the VR HMD, and two 14mm coin vibromotors that we mounted them inside the VR HMD headphones. As you can see in the top right image, it's possible to put the vibromotors inside ears for VR HMDs without headphones. The vibromotors transfer the vibration to the user's ears. In the bottom right image, you can see the connections of Ear VR to PC or mobile phones. Ear VR needs a 3.5mm headphone jack for transferring audio to Arduino and a USB connection as Arduino power supply. In this slide, you can see the main structure of Ear VR that consisted of two main parts, hardware and software. You saw the hardware part in previous slide. In the software part, we have the Arduino code that performs a frequency analysis on input stereo sound channels and finds the channel with higher intensity. Then it controls two vibromotors based on the higher intensity of the audio in each channel. For example, if it finds that the left channel is louder, then it turns on the left vibromotors and vice versa. Therefore, the user knows the direction of the incoming sound based on the vibration of the vibromotors. We also consider some thresholds for some special situations. For example, if the intensity is equal in both channels, then the vibromotors will not vibrate. In this case, there are two main situations. One, the sound source is in front of the user with the same distance from both ears, which is very easy to find because the user can see it. Two, the sound source is behind, above, or below the user, So, user, pay attention to above or below. There are more technical details about the frequency of input sound and the vibration intervals for vibromotors that you can read it in our paper. EarVR has two main requirements. The first one is that VR applications must have an option to mute background music. And the second one is that developers must use 3D audio in their applications. For designing our user studies, first we designed a pilot study to test our idea about using VR among deaf and hard of hearing people. The goal of pilot study was to investigate if deaf and hard of hearing people can identify the direction of sound by using ear VR and their feeling during the VR experience. After that, we formulated some hypotheses based on the results of the pilot study. Then we designed our main study and usability study to find if our hypotheses are supported or not. The goal of these studies was to study our methodology in real VR scenarios. For pilot study, we recruited two groups of people. Group 1 with 5 persons without hearing problems and Group 2 with 5 persons with no hearing in both ears. We designed a very simple VR game and asked the participants to play it. In this simple VR game, the user was placed in the center of the environment and 4 speakers, 4 3D objects, were placed around him or her. In this experiment, one speaker starts playing a continuous sound, a looping wave, at a random time, and the user must select it by using VR controller. If the user selects the correct speaker, the next random speaker will start playing a sound. This process will continue 4 times. After selecting the 4th speaker, the task completion time of the user is recorded, which shows the user's success in completing the given task. If the user selects a wrong speaker, the task will be over and it will be recorded as a failure. Each participant played this game with 2 conditions, with ear VR and without ear VR. Users can play the game 3 times in total in each condition if they want. In this slide, you can see the results of our pilot study. Players without hearing problems won in all their tries, without game over in both without and with ear VR conditions. For this group, the average completion time without ear VR was 5.84 seconds, and with ear VR, it was 5.34 seconds. Now, look at the results for deaf and hard of hearing people. Without ear VR, none of them were able to complete the game successfully even once. But with ear VR, all deaf and hard of hearing persons were able to complete the game at their first attempt, and the average completion time was 5.7 seconds. If you notice to the average completion time of deaf and hard of hearing people with ear VR and the average completion time of persons without hearing problems without ear VR, you will see that these average completion times were very close. The behavioral state of deaf and hard of hearing people during the test showed us that they were much happier and more excited with ear VR than without. We formulated the following hypotheses based on the results of our pilot study. 1. Ear VR helps deaf and hard of hearing people to locate sound sources in the VR environment in a time very close to persons without hearing problems. 2. Using ear VR, deaf and hard of hearing people can complete sound-related VR tasks like persons without hearing problems. 3. Ear VR encourages deaf and hard of hearing people to use VR technologies more. 4. Ear VR improves the task completion time for persons without hearing problems. For our main study, we recruited 40 volunteers in 2 groups of 20. Group 1 included 20 persons without hearing problems, and Group 2, 20 deaf and hard of hearing persons with no hearing in both ears. We divided each group of 20 into two groups of 10. Subgroups 1.1 and 1.2 included people without hearing problems, and subgroups 2.1 and 2.2 deaf and hard of hearing people. We asked the members of subgroups 1.1 and 2.1 to do the given tasks without ear VR, and subgroups 1.2 and 2.2 with ear VR. We designed two tasks for this study. Task 1 called Find the Cube, and Task 2 called Find the Correct Cube. In Task 1, 10 identical cubes are spawned one after another in random positions in the VR environments. Each cube produces continuous 3D sounds. The user is placed in the center of the room and can only rotate around to find the cube. Each cube will be eliminated after getting selected. This process will continue until all 10 cubes are selected. Finally, the user's task completion time will be saved for each user. There is no game over mechanism in this task, and all users can complete the game at the end. In Task 2, 10 identical cubes are spawned simultaneously in random positions of the VR environment separated by walls. Only 5 of these 10 cubes will generate continuous 3D sounds. The cubes are identical and have no signs to show the user which one is generating sounds. For this task, the user can move around using teleportation to search the areas behind the walls. This task is completed only if the user finds the correct 5 cubes. If the user selects a wrong cube, the game will be over. Users can play the game between 1 to 10 times. The time that each user can spend in the game is limited to 5 minutes. The number of plays, wins, and game overs are recorded for each user. The task completion time is not important for this task. Here you can see Task 1 results for both groups of participants. This chart shows the completion time of Task 1 for Group 1 and Group 2. Members of Group 1 were able to complete the task with an average completion time of 14.9 seconds without ear VR and 12.6 seconds with ear VR. Members of Group 2 were able to complete the task with an average completion time of 29.6 seconds without ear VR and 14.7 seconds with ear VR. Analysis of the results for this task showed us that deaf and hard of hearing people were able to complete the task much faster with ear VR, very close to average completion time of persons without hearing problems without ear VR. Now let's see Task 2 results of our main study. In this slide, you can see the results for Group 1. Please notice that the task completion time is not important for this task, and we focused on number of plays, wins, and number of game overs for each user. As you can see, by using ear VR, the total number of plays and total number of wins increased, and the total number of game overs decreased. Here, you can see the task results for Group 2. Nobody in this group without ear VR could complete or finish the task even after several tries, whereas everyone with ear VR could complete the task or win at least 3 times. Analysis of the results showed us that the total number of plays and wins increased significantly, which demonstrate that deaf and hard of hearing people have much more desire to play the VR game with ear VR. To support our claims in real VR scenarios, we designed a usability test to study how efficient ear VR is among deaf and hard of hearing people. We decided to develop a VR game that supports ear VR's requirements. In this game, players get scored by eliminating the enemies. We asked all 20 deaf and hard of hearing participants from previous tests to join and play this game with ear VR, and all of them participated in this test happily. At the end, we asked all 20 participants to fill in an anonymous survey about their experience of playing the VR game. We designed this test to study ease of use, satisfaction, effectiveness, and desire to use VR with ear VR among deaf and hard of hearing people. Here you can see the results of our usability study for deaf and hard of hearing people. Please notice that the results of without ear VR blue lines, are based on participants' experience from previous tasks. The analysis of the results demonstrated us that deaf and hard of hearing people find ear VR very easy to use. The satisfaction rate was very high because they believed that ear VR made VR applications more enjoyable for them. They also rated the effectiveness of ear VR very high because they believed ear VR can help them to complete tasks in different sound-based VR applications. And finally, the desire to use VR with ear VR was very high among them. As a summary, in this presentation, we introduced and evaluated ear VR as a mountable device for different VR HMDs. Ear VR provides the direction of the sound to the user using two vibromotors placed on the user's ears. Based on our results, we found that all our hypotheses are supported. Ear VR helps deaf and hard of hearing people to complete certain VR tasks that they were not able to finish before, and also improves their experience in VR. It encourages them to use and enjoy VR technology more than before. But it's just a beginning for ear VR, and further studies are required to determine how ear VR might be used in the deaf and hard of hearing community. For the future work, we are going to test ear VR in complex VR environments to investigate more parameters. Also, we are going to analyze different sounds in VR environment and adding sound visualization techniques to the ear VR. We hope to inspire VR software and hardware developers to create more ear VR compatible applications and also use this system in their future VR HMD designs so that deaf and hard of hearing people and even persons without hearing problems can enjoy the benefits of ear VR. Thank you so much for joining my presentation. If you have any question, please feel free to ask.
Okay. Thank you very much for the nice presentation. We have some questions here. The first question is by Roshan. He's asking how was the comfort of the vibrations of a prolonged use for the DHH users?
Well, actually, we used very flexible and soft plastic shapes for the vibromotors, that when the users put these vibromotors in their ears, they didn't feel any bad feeling or something like that. But for a long term, for a long time, for example, using this, actually we didn't tested it because I think it's much more like when you put the headphone on your ears and when you use it for a long time, well, you will be a little uncomfortable. So, but in the during of these tests, we couldn't find any bad feeling from the person. So this is the first question.
Thank you. Then we have a question from Brooke Bowers, who is asking, this is a fascinating device for increasing accessibility to VR. VR applications typically rely on a combination of visual and auditory cues. Did you consider measuring the incremental benefit of auditory cues above visual cues?
Well, actually, in our experiments, we focused on sounds and to find the direction of the sounds based on the vibration and the haptics feeling on the ears. So, but for our future works, we are going to add the visual effects and combine also the visualization of the sounds on the cubes, on each cube. And we want to know that if the results will be different or not. And I think it will be much better because as as Brooke said, the visualization is also important to find this direction of the sounds or the cues. And I think in the future work, we will notice that if it's good or not. So.
Yeah. Thank you. And another question is, can you elaborate on the kind of sound that was used in the find the cube task?
Sorry, so the sound was continuously playing. In the find the cue task, you said the sound was continuously played for each cue. Oh, that was a loop sound, which is in the Google Resonance Audio SDK. That if you use it, if you play the Google Resonance Audio, you notice that there is a continuous loop wave sound that plays continuously. So there's not a special sound that played. That's it.
And the last question, have you tried to vary the intensity of the vibration to convey more information about the type of sound?
Mm-hmm. Actually, for the vibration side, we tried some vibration intervals before we did the main tests, and we fix it. We find the vibration that is actually better for also if the deaf and hard of hearing people, and they feel the vibration better on their ears. So we fix it. But in the future work, we are going to actually add some. We are going to analyze different sounds in the environment and add different vibration intervals to vibromotors. But we need some more powerful processor, and we should think that if Arduino can handle it or not.
And very nice question by Rob Lindemann. Nice work. Will you put the Arduino code somewhere?
Oh, yeah, it's a nice question. Unfortunately, not yet, because I'm still working on this code, and because I add some tricks actually on frequency analysis and amplitude in this code. But maybe in the future we can put it. Maybe we can make it open source and put it somewhere. But if you have any question about the code, you can send me and contact me, and I will help more.
Thank you very much again
You're
for
welcome.
the nice talk. Thank you. And
Thank you
now
so
we
much.
move to the last presentation of the session, which is entitled Outdoor Sound Propagation Based on Adaptive FDTDP. And the presentation is given by Xingguan Liu.
Have the opportunity. Hello everyone, I'm pleased to have the opportunity to present our paper, Outdoor Sound Propagation Based on Adaptive FDTDP. Next, we will introduce from 5 aspects: introduction, related work, method, experiment, and conclusions. First, introduction. Realistic simulation of sound propagation can improve users' immersion in games or VR, outdoor environment, or accounts for large parts in the virtual environment. Therefore, realistic simulation of outdoor sound propagation is necessary. Some researchers have proposed sound propagation techniques that can be applied in both outdoor and indoor scenes. However, these techniques do not consider the two key factors affecting outdoor sound propagation: the inhomogeneity of the outdoor atmosphere and the grid effect. In this paper, we propose an adaptive FDTDP method which can quickly simulate sound propagation in outdoor inhomogeneous atmospheric scenes with an impedance of grid. Second, related work. Outdoor Sound propagation has been widely studied in the field of acoustic. The methods of solving the problem of outdoor sound propagation include numerical acoustic method and geometric acoustic method. Numerical acoustic methods calculate sound propagation by numerical methods to solve wave equations including FFP, FDTD, PE, and FDTD, PE. FFP and PE are frequency domain methods. These methods are accurate but slow. Geometric acoustic methods including Gaussian beam method and ray tracing method, which calculate the speed is fast, but the low frequency domain cannot be simulated. In computer graphics, sound propagation simulation needs to be fast enough to interact in VR and games. However, in the field of acoustic, it is difficult to achieve interaction with sense. Interactive sound propagation simulation often use computation to obtain the acoustic kernel of a static sense, and take this kernel to calculate the pulse-response function of the moving length, reaction, and runtime. Also, some of these methods, ARD and the equivalent source method, could be applied to sound propagation in outdoor atmosphere. They did not take into account atmospheric inhomogeneity, the Gould effect, and law reflection. And the method. As shown in figure, the algorithm is divided into 3 stages: simulation, encoding, and sound rendering. In the simulation stage, we propose an adaptive FDTD-PE method to simulate sound propagation in outdoor sense. The 3-dimensional space is divided into a series of 2-dimensional planes. According to the location information of sound source and obstacles, we decompose the 2-dimensional planes into the near-source complex regions and the far-source regions. We build an adaptive FDTD solver to simulate sound propagation in near-source complex region and an adaptive PE solver in far-source regions. In the encoding stage, we specially designed an encoder to process the sound pressure data of outdoor sound propagation, which can greatly reduce the memory of sound pressure data and simulate outdoor sound propagation more accurately. For the near-source complex region, we extract the ER/IR in frequency domain from sound pressure data and set the corresponding time of DR to 0. For far-source region, we first transform the frequency domain sound pressure data into time domain, and then we do the same encoding as near-source complex region. Finally, we design a function to feed the sound pressure data. In the sound rendering stage, according to the listener's location, the decoding method is selected to a built-in ER and IR. In far-source regions, we built the IR and listen the position by the fitting function, the intentional ER and the intentional IR. Finally, our realization is related in the frequency domain. Next, we will introduce every stage in detail. In the simulation stage, in order to use FDTD-PE method to simulate 3-dimensional sense, we first provide 3-dimensional space, separational and liberational, as shown in figure. In figure A, because the PE methods depend on the propagation direction of sound waves to simulate, we transform the sense information from rectangular coordinate system to the cylindrical coordinate system. The 3-dimensional space is decomposed into n planes, as shown in figure B. According to the FDTD-PE plan partition theory, AG is decomposed into complex near-source region BG and two far-source regions CG and CG prime. And we extract the Gould change curve HR prime from the sense information of AG as shown in Figure C. Next, each plan is calculated. We determine the simulation time length Tg of FDTD method, and the time single of sound pressure in BG region is calculated by FDTD solver. At the junction of BG with CG and CG prime, FFT is used to convert the time domain sound pressure single into the frequency domain, which serves as the intention fields. After determining the error size, use PE solver simulation. The CG and CG prime regions are simulated by the PE solver. Here is the equation for Tg and L prime. Tg is time length of the impulse response calculated by the FDTD method in region BG. R1 is the length of region BG. R2 is the total length of the area with obstacles in BG. It is unnecessary to calculate the sound pressure value in all areas of CG. We only need to calculate part of the sound pressure data for fitting. We assume that the height of region CG is h and the length is r. Here is the formula we used. In the encoding stage, we needed to sample and encode the sound pressure data to reduce the use of memory space. We input the sound pressure data of region AG. First, the data is proposed by downsampling, and then the IR is gotten. In BG region, we extract the peak value of time domain sound pressure single to IR. Then IR is separated into ER and IR. ER of each sampling point is saved. After increasing the peak dysentery at the sampling point, IR is converted to the frequency domain for saving. In CG and CG regions, the frequency domain sound pressure data is converted into time domain. Then we get ER and IR by using the same method as that in region BG. Next, experiment. We tested our method in these three representative outsourcings. The performance of our method was compared to other state-of-the-art methods as shown in table. As shown in figure, in the same sense, we simulated the sound propagation of rigid growth and the porous medium growth, respectively. According to the experimental results and characteristics of various methods, we compared our method with FDTD PE, FDTD, and PE in terms of memory, computing speed, and applicable scenario type as shown in table. To further access the realism and accuracy of sound results by our method, we designed the user study. We show our question and the results of user study in figure. Finally, conclusions. There are three main contributions of this work, including an adaptive FDTDP solver, a function fading encoder, and an function sound rendering method. That's all for my presentation. Thanks for your listening.
Thank you very much for the presentation. We have some questions in Slido. They're quite similar. The first question is about does the method work in real time and what is the speed of this method, basically?
Yeah, about the speed of a method. For runtime, the method can be in real time. It's due to the permutation. So it can be achieved real time. Thanks.
Thank you. And does the method support spatial sound rendering?
Yeah.
It seems that there is no binaural sound in the video.
Yeah. In our method, we didn't incorporate the spatial sound, and we pay more attention to the sound propagation. So in the future work, we will to include the spatial sound. So it's one of our work to include. Thanks for this question.
Okay, thank you very much. I don't see other questions in Slido, and I think we are also running out of time for our session. So I would like to close then the audio session, and thanks all the speakers of these 4 interesting papers. If you would like to join the hubs to discuss more audio-related topics, otherwise, thank you for your participation and have a good lunch or afternoon or evening, depending where you are located. Thank you very much. Bye-bye.